Suppose you have this circuit where you have one battery and one resistor. This is called a single loop circuit because everything is in one loop. All right. And so this circuit is a single loop circuit, and any circuit which can be ultimately reduced to this is also called a single loop circuit. So that means our very complicated Wheatstone bridge circuit over here is also when the middle part is not connected, is also a single loop circuit, because we did a few manipulations and eventually we brought it in diagram 3, we brought it into the form of a single loop circuit. So this circuit, this circuit and any circuit that can be reduced to this form is called a single loop circuit, right? Now, so single loop circuits can be analyzed the way that we just did, right? So there is nothing wrong with that. So we can totally do that. But sometimes you can have circuits which are not single loop circuits. And on the slide, I have some examples of that. So these circuits are called multi-loop circuits because you cannot reduce them by combining all the resistors. You cannot reduce them to a single loop circuit. So for example, this one, these two can be combined into one, no problem there. But what about this stuff over here? You cannot just combine them because the R2 and the R3 are not either in series or in parallel, and there's a battery in between them. So these are called multi-loop circuits. So multi-loop circuits are when you have multiple loops and you've got batteries inside these different loops. So those circuits cannot be reduced to the single loop form using the rules of combining resistors in series and parallel. So you need more sophisticated tools to analyze multi-loop circuits. And there are many different tools that have been developed to analyze these circuits. The simplest one, and in fact the only one that I know because I'm not an electrical engineer, is Kirchoff's rules. That's what we're going to study now. So Kirchoff's rules is a technique to analyze arbitrarily complex circuits. So no matter how complicated the circuit is, what horrendous combination of batteries and resistors you have, you can always use Kirchoff's rules to analyze it. And by what do I mean by analyze the circuit? It means finding all the currents in every branch in the circuit, like finding all the currents throughout the circuit. That's what analyzing the circuit means. So that's pretty much what we did in the problem that we just solved. We found all the currents in all the branches of the circuit. So Kirchoff's rules is what you use, is one tool that you can use to analyze analyze circuits. So let's talk about Kirchoff's rules. So remember that Kirchoff's rules are just an algorithm, which means that they're a set of rules. If you follow those rules, you are guaranteed to get the correct answer. You don't need any brain power to execute them. Just have to be a bit careful, making sure you're not making any arithmetic errors. But you just have to follow those rules, and then no matter how horrendously complicated your circuit is, you will get the answer. You're guaranteed. It might be a lot of work, but you will get the answer. So you don't need any brain power. It's just just work. So there are two rules. First one is called the junction rule, and the second one is called the loop rule. All right, so let's look at the junction rule first. So the junction rule says that the sum of all the currents entering a junction must equal the sum of all the currents leaving it. So let's look at that. It's actually quite intuitive. So suppose you have a junction over here in a circuit. This is a wire and a current is coming into this junction. Let's call that I1. And this is another, and let's also give this a number. Let's say it's 2 amperes. And you've got another current I2 also coming into this junction. Let's say that that's 3 amperes. And then you've got this current I3, which is leaving the junction. And let's say that this is 4 amperes. And you've got another current I4 leaving the junction. Let's say we don't know what that is. Okay, we can figure it out in just a moment. Now, what Kirchoff's loop rule says is that the sum of all the algebraic sum of all the currents at a junction, entering the junction or leaving the junction, has to be 0. That's quite intuitive why that must be the case, because let's look at the 2 ampere current first. 1 ampere just means coulombs per second, right? So the 2 ampere current is bringing in 2 coulombs every second and dumping it into the junction, right? So the I1 is dumping 2 coulombs per second into the junction. I2 is dumping 3 coulombs per second into the junction, right? Now the junction is obviously not storing any current. It's not possible for charge to accumulate at the junction, and the junction also cannot manufacture charge. So that means any charge that's being dumped into the junction is immediately being cleared out from the junction as well. So that's what I3 is doing. So I3 is clearing out 4 coulombs out of the junction every second. So what do you think I4 is?
1.
Yes, exactly. So I4 must be 1. So the total amount of current per second, the total charge being brought into the junction by the incoming currents must equal the total charge being removed from the junction by the outgoing currents, because you never have charge being built up, charge being stored in the junction. That can't happen. Is that clear to all of you? So that if you write that as a, if you want to write that as a rule, or as an equation first, and then we'll make that into a rule. It means I1, and if we just decide that incoming currents are positive and outgoing currents are negative, then I1 plus I2 minus I3 minus I4 must be equal to 0. That makes sense? And if you want to write this as a general rule, sum over all the currents, I running over all the currents, is equal to 0. And here we are using the convention that incoming currents are positive, outgoing currents are negative. Everybody clear about that? And that's it. So that's Kirchoff's loop rule. Sum of all the currents is equal to 0. Everybody clear about the loop rule? All right. Now the junction rule, sorry, that's the junction rule. I always get these two names mixed up. So this is the junction rule because it pertains to a junction. Now we're going to talk about the loop rule. The loop rule is also quite simple conceptually. So the loop rule says that suppose you have some kind of a circuit, some circuit, it might be a very, very complicated circuit. You might have plenty of batteries, resistors, whatever. So now if you just consider any point in the circuit, like let's consider this point A. This point has a certain value of potential, right? So there must be some potential at this point, some value of potential at this point, VA. And suppose that's 23 volts. I'm just making up a number here, right? Now, the potential must be a single valued function of position, which means at that point A, that potential will stay the same. The currents are not changing. So we are always looking at situations where the currents are all fixed. So at a certain point in the circuit, the potential must have one and only one value, right? So if I say that the potential at A is 23 volts, it cannot simultaneously be 36 volts or 125 volts. It cannot. I mean, this doesn't make any sense. So if I say that the value of the potential at A is 23 volts, it's always 23 volts. It cannot be anything else. That clear to all of you? So the idea is that at a given point in the circuit, the value of the potential is unique and fixed. It cannot be multiple values. So what does that mean? What's the consequence of that? Suppose, let's look at a complicated circuit. I have an example over here. Okay, so let's look at this circuit that I've drawn here. Let's call this point A and this point B, right? And this point C and this point D. All right, this circuit might be part of a much more complicated circuit. We don't care about that. Let's say that we start at A, right? And then we go around in a loop from A to B and then B to C and then C to D and then back to A. And the value of the potential at A has some particular value V sub A, right? Suppose we are going around this loop, and as we are traversing the loop, we compute the changes in potential. So from A, let's say we go to this point P, and there must be a change of difference in potential between A and P because there's a battery in between them. And then we go from P to B, there must be a difference in potential between P and B because there's a resistor and a current is flowing through that. So B must be at a lower potential than P. So suppose we keep track of all the changes of potential that are happening. if we go around in a loop and come back to A, what must all those changes add up to?
0.
Yes, exactly. Because the potential at A is the potential at A, right? So if some changes have been happening, but we come back to A, all those changes have to add up to 0. Everybody completely clear about that? To give you some examples of that, this is quite a trivial concept. It's nothing profound about this at all. So suppose you look at your bank balance in the morning one day, and you note what the number is for your bank balance. And then let's say that day a lot of financial things happen to your bank balance. You deposited a few checks, those cleared, and the balance was added to your account. Maybe you had lunch and paid with your debit card, so some money went out of your account and so on. And then you look at your bank balance at the end of the day, and you see that it's exactly the same as what it was at the beginning of the day, right? Somehow that worked out that way. So after all these transactions happened, your bank balance is still at exactly the same value that it was in the morning. So the only conclusion is that somehow all the money that was added and subtracted, all of those changes added up to 0, and that's why the net change is 0. That clear to all of you? And so that is an example of this is an example. This is just like that. So the potential at A has a certain value. So if you go around in a loop, but you make sure to come back to A, then all the changes that happened along the loop must equal 0. Everybody clear about that? So this is called the loop rule. Oh, it's here. The loop rule says that the sum of the potential differences across a closed loop is always 0.